will be looking for an internship this coming summer, so if anybody's looking for a great intern, we'll come for it.
University. Today I will present our work titled Hindsight, Understanding the Evolution of UI Vulnerabilities in Mobile Browsers. This is a joint work with my colleague, Alexis Staff, and my advisors, Nima Ahmed and Mika Borges. In recent years, as the popularity of mobile operating systems like iOS and Android, people are relying more and more on the mobile devices for their daily activities, such as shopping, banking, and social media. So the smartphones are gradually overtaking the traditional desktop platforms. It is reported last year that over 52% of the worldwide internet traffic is now from mobile platforms. In addition, people now spend a majority of their digital minutes on these mobile platforms. Mobile devices really encompass a variety of mobile applications, such as the mobile web browser. These applications typically account for the significantly increased internet usage. However, there are some idiosyncrasies of the mobile devices allowing for novel attacks against mobile web browsers, such as the limited screen real active, the error phone info massive, and the limited computing power. Let's first take a look how the limited screen size can expose novel attack surface. The website identity rendering address bar is crucial for our secure web browser because people may rely on it to identify website source. However, the space for address bar is really constrained by mobile devices' limited screen dimensions. These three groups of figures demonstrate how top and bottom browsers show website identity when rendering a common website. The top browsers are secure and the bottom browsers are vulnerable. The figures on the left are showing the case that browsers are rendering a website with long URL. The bottom browser is vulnerable by truncating the long URL and cutting off the domain name portion of the URL, so it is kind of misleading. The bottom browser in the middle is vulnerable by giving privileges to title instead of URL, so malicious website can easily control the content in the address bar and better social engineering against users. The bottom browser on the right is maximizing the space for web page content by hiding the whole address bar. So without website identity in address bar locating some sensitive operations, the users can be easily attacked without notice. Fortunately, this problem has gained much attention from the community. Be aware of the negative effects of the change in mobile devices. These related works have made manual measurement over mobile browsers in terms of the display of URL, security indicators, and so on and so forth. However, there's a common limitation in these related works. Their experiments were done once and were done manually with a limited number of browsers, so they can only capture the security issues at the time of measurement and only over a few browsers. But the truth is, if you search browser in Google Play Store, you will be surprised by hundreds of browsers, each advertise unique features. So users' choice of mobile browser is no longer limited to several prestigious browser vendors, but instead they prefer to install others with the features they like. Apart from that, these browsers are usually updated frequently, so the ones in manually prepared without does not skill. When manual labor does not work, we usually turn to automation. We design and develop an automated browser-agnostic vulnerability testing framework called Hindsight for mobile browsers. The high-level approach of our work is we generate as many mobile browser-specific attacks as possible, and then we collect the mobile browsers available in the Android market and download as many release versions as possible. With Hindsight, we can evaluate the vulnerabilities by automatically exposing the mobile browsers to the attacks. Through the manual results, we can analyze them to understand the evolution of mobile browser security. We start with investigating mobile browser-specific vulnerabilities and generate 27 attack building blocks, which can be used as a standalone or information information to launch some attacks. These attack building blocks, also called APBs, are then moved into 5 classes. In security indicator class, we test if a browser shows appropriate security indicators, for example, for mixed content website. As for the URL class, we test if the browser shows a URL in a confusing way, for example, by hiding the domain name. As for the address bar class, we test if the browser hides its address bar when users are interacting with the web page, for example, submitting the form. As for the event routing class, we test if the browser directly draws the touch events on overlapping elements. Finally, for content class, we test if browser load or execute potentially insecure content. If you are interested in more details about the attack building blocks, please also check this table in the paper. So given the APBs I just mentioned, you may have a basic concept of the UI vulnerabilities in mobile browsers, but you may still wonder how these vulnerabilities can be abused in real-world attack scenario. So imagine a case you are reading an interesting article in Chrome, so you go all the way to the end of the story, and you want to share the story with your friend. So you click this button, and you believe you are redirected to Facebook, so you provide your username and password. But the truth is, you're disclosing your credentials to a third-party website. So the problem behind is, malicious website can easily mimic the process of navigation within a website. But because the browser doesn't provide the URL or the website identity of the website, the users can be easily confused with the source of the website. Given the APBs, the APBs I just mentioned are designed to be evaluated on particular browsers. So the next step is collecting the mobile browsers to test. We start with crawling the mobile browser families from Google Play Store. So through manual filtering, we find 128 different mobile browser families available in the market, which are ranked according to the number of installations. But because Google Play Store only provides the latest version of the browsers, so we resort to third-party websites in order to download the history versions. Initially, we download over 4,000 browser APKs from 7 different sources. According to a few steps of filtering, we finally arrived to the 2,324 browser APKs that are being tested. Our data collection is done as of August in 2016. Our data set has a good coverage in terms of the number and the range of the browser versions. So, for example, in Chrome, we have the oldest version of 29, which is close to the first version officially released by Google Chrome. We also have the latest version at the time of data collection. And averagely, for Chrome, we have more than 10 versions per year. In order to evaluate these browsers, we also need to extract some metadata from them. On the one hand, we need to get some usage metadata, for example, the SDK version for assigning the browsers into appropriate Android devices for testing. In addition, we also need to obtain some release timestamp of every browser version for taking the evolution analysis. With the APBs and the mobile browsers, Hindsight is designed to evaluate browsers' vulnerabilities. So Hindsight mainly consists of 4 steps. For step 1, we take the browser APK as input and assign it with appropriate Android device according to the SDK assignment algorithm, which can ensure the browser function properly. Then the browser will be installed on the given device, and the Hindsight will help to prepare it with loading arbitrary web pages. But we find many browsers are rendering a few splash screens, which will be the usage terms, the usage tips, and some new features that will be rendered in advance of loading a web page. And we need to provide some user interactions, such as tabs and swaps automatically for guests through them. So we implement the splash screen bypassing algorithm, which can work with this problem. When the browser is ready to load arbitrary web pages, the testing logic will request the web pages of ABBs from a web server and provide necessary user interactions on the web page content to trigger certain browser behaviors. Finally, the evaluation logic will take the input of server logs, the UI dumps, and the screenshots to determine if the browser is vulnerable to particular ABBs. To implement such a browser-agnostic framework, we usually need to solve a few challenges. For sensing the UI vulnerabilities, we need to identify the appearance of required elements. But even by loading a common website, different browsers may behave quite differently in terms of the location and the display of the address bar and the rendering of website content. So we implement a browser-agnostic UI analysis component. The UI analysis involves analyzing both the application-level UI and the web page-level UI. For application-level UI, we can use the UI monitor to grab the UI dumps of the content on the current screen. But because in some cases, we find the UI dumps that we got in this way may be not consistent with the content on the screen, so we use OCR to improve the result. When the UI dumps are grabbed, we need to identify the location of particular elements. But we find there's no common way to locate some resources of interest, such as the favicon and padlock. So we implement a multi-scale image comparison algorithm to identify their location on the screen. As for the web page level UI, there is a contention. On the one hand, it is required to provide some user interactions on the web page elements to trigger certain behaviors, but there's no WebDriver for all possible mobile browsers to identify the web page DOM. In addition, there's no mapping between web page DOM and the device coordinates, so we use OCR to analyze the web page level UI. But even by using the existing tools, we need to overcome the limitation they have because we need to make the UI analysis work in an accurate and stable way. The splash screen bypassing is another challenge. The splash screen are few pages rendering in advance of loading a web page. So these screens could be the terms and any elements that the browser want to display in advance of the page for the first time of installation. It is required to provide some user interactions to get through them. But while doing this automatically, this is difficult to predict what actions and what combinations of them are required. For instance, Google Chrome may request several taps on the buttons to accept the terms, whereas the Power browser may request several times of swapping in order to learn the features. So we implement a splash screen bypassing algorithm, which can successfully bypass at least 70% of these splash screens. This video shows how Hindsight works in parallel to bypass the splash screens, to provide the automated user interactions on the web page elements, to evaluate the ABBs. So we run Hindsight with 4 real Android devices, each equipped with different versions of Android system. By running the experiment in Hindsight, we successfully exposed 2,324 browsers to 27 attack building blocks. And finally, we generate 62,000 measurement reports. In order to verify the correctness of our framework, we write script to automatically produce the self-contained web pages, which includes the screenshots and the results for every browser and ABB tuple. So then the human expert can review the measurement result in order to identify any evaluation errors. Among the 62,000 measurement report, we find the error rate is 3.6%, which includes the errors captured by a human expert, the errors captured by the Hindsight framework. So in analysis stage, we take these errors into consideration. We apply both the upper bound and lower bound. The upper bound means all the errors are marked as vulnerable cases, whereas the lower bound means all of them are marked as secure. So let's see the evaluation result. This figure shows how the number of vulnerabilities change as the fraction of browsers aggregate. It is found that over 98% of the browsers are vulnerable to at least one ABB, and half of them are vulnerable to more than 12 ABBs. Browser versions may not be always evenly distributed among the browser families, so we analyze what fraction of browser families are vulnerable to what classes of ABBs. In this figure, a browser family is vulnerable to a class of ABB if at least one version inside the browser family is vulnerable to at least one test case inside inside the class of the ABB. So it is found that most browser families are affected by the URL-related ABBs because in most of these browser families, they may fail to to display a non-misleading website identity when rendering a website with long URL. In addition, we also compare the older versions with the latest version of the browser families. We find in almost all the classes of the ABBs, the latest version is not necessarily behave better than the older versions. People may expect that a browser's version update can gradually improve its security. We undertook a longitudinal analysis of vulnerability to analyze, for example, in this figure, we analyze the average number of vulnerability change as the years change. So this figure shows in the shadow line, it denotes how the general browsers, which involves all the browser families, are developed over the years. The general browsers are more vulnerable in some years, whereas in some other years, they become more secure. But we find the change pattern for the particular browser families, such as the Chrome and Firefox, they may behave quite differently. Further, we also investigate how is the popularity affects a browser's vulnerability. This figure shows what fraction of the browsers within each rank level is vulnerable to different classes of VBs. We find the most popular browser, like Chrome, in rank 1 is not more secure than the less popular browser families. For example, the Shark browser in rank 13 we find the Shark browser is not vulnerable to address bar related ABBs because it can always stick the address bar on the top of the screen so that when users are taking some sensitive operations, for example, submit a form, they could have the way to identify if the website is the one that they want to interact with. Finally, we also take an evolution analysis over the browser families. We order all browser versions of a family in terms of the release time and observe how the vulnerability evolves as version update. We observed mainly 6 stable evolution patterns. For example, we find a temporary secure pattern appearing in Dolphin browser when it displays a website with long URL. In an older version, for example 8.5.1 on the left, the browser is vulnerable because it truncates the long URL and it just displays the subdomain part of the URL. So it looks like this website is from PayPal.com. But when they turn to a middle version, which is 11.4.9, the browser becomes secure because the browser can highlight the domain name part of the URL so that the website can know the real nature of the website. But the browser have the regression because it becomes vulnerable again when they go to the later versions. Apart from the temporary secure pattern, we also observe some other undesirable evolution patterns. For example, in URL and security indicator class, we find some patterns dominate. For example, the always vulnerable pattern and the evolution from secure to vulnerable pattern. In addition, we also observe some other dangerous patterns which appear in almost all ABBs. For example, the temporary vulnerable pattern and the regression from secure to vulnerable pattern. To conclude, this work, we want to highlight that the UI security of mobile browsers still require more attention because attackers can take advantage of mobile browsers as synchronous to attack or social engineering against users. So we implement Hindsight, which the first automatically dynamic analysis browser agnostic testing framework for gauging the mobile browser security. According to the experiment, we find more than 98% of browsers are vulnerable to at least one UI attack. In addition, the newer version of mobile browsers and the popular browsers are not necessarily behave better. Finally, we find the security regression is a very common case in many browser families. So thank you, and I'm ready to take your questions.
So anyone with questions should please feel free to step up to the microphone. But I actually have one. I think I'll start off and take the session chair's prerogative. So I'm kind of curious about what sorts of errors you actually encountered in practice that your tool had generated, where the humans disagreed with the tool. Was there any sort of pattern in terms of what you'd observed there, or was it mostly random?
Sorry.
So when you actually saw errors, you pointed out that Hindsight in some cases made mistakes, and then humans actually caught those errors for about 3.6, I think, percent of the case, or something like that.
Yeah.
Was there any common theme there? Was it missing certain types of errors in particular, or what was the nature of the errors that were made by the tool?
Oh, so the problem is if we can analyze the elements on the screen without any problem, then there will be no problem with the evaluation with the identify the uh, with the evaluating the ABBs. But because we are using the OCR and we are using the UI automator, we try to overcome the limitation they have, but it's still in some cases that we cannot get the perfect UI analysis result. So that's the problem behind the error rate we have.
Okay, I see. Yes, please step up to the microphone, and if you could just state your name and affiliation.
Hello, I'm Kaur from Estonia, government official. So the question is, who should be using this research? Is it targeted for policymakers, for browser uh, software developers? Who should actually be taking this information and act on this? What's your opinion?
Yeah, like the video, like the attack video I just showed, like the video I just showed, in the case that if the attacker can leverage the vulnerability of the browser families of different browsers, they may combine different attack building blocks we have to take like maybe a stronger phishing attacks, or maybe they can do the privacy, steal your account information. So they can use this kind of like pieces of the vulnerabilities that we find in the mobile browsers to social engineering against the users. It's just pretty like the case that I just showed in the video. Is that the question you want?
Sort of. Thank you.
Okay.
I have two questions. The first one is could you give me any good example of the error in the security indicator? So
Uh-huh.
what was the problem and what was the errors in security indicator? And the second question is that you have seen there are some vulnerable years. I mean, in time,
Uh-huh.
some there was some secure year. Was there any security event or why there is some differences in security?
Okay. For the first question, we find even if we can say that the desktop browser can differentiate like the valid HTTPS, the broken HTTPS, but we find in many mobile browsers, they like for example the UC browser, we find they have no difference with the valid HTTPS and the broken HTTPS. For example, one of the broken is probably the mixed content website. So they can't differentiate that. So the users have no way to know if they are if the website is transported in a like encrypted way. So this could be the problem. And for the later question, I think because the year that we group is in terms of the release time. So it's basically that the different browsers are developed quite differently. But for mobile browsers, we can also say because they are using the web view, many browsers are developed with the web view. So we can also maybe like in the future for the security features of the browsers, we can analyze if the problems that we can find can be from the problem of the web view. So that could be like according to the special security event. But in this case, it's just like individually developed. So it's just browsers personally design decision. So it's not related to special events, security event.
Thank you very much.